more continuity. Today we're going to look at continuity functions over their domains. So, for example, exponential functions, arctangent, sine, and cosine, they're not only continuous over their domains, they're continuous for all real numbers. Like rational functions, root functions, trig functions, inverse trig, law functions, they are all continuous over their domains. So if you could find out the domain, it could be really useful to find where it's continuous. So let's look at example 4, part A. We're going to give the intervals where these functions are continuous by finding their domains. Now we know x squared is a polynomial function is continuous for all real numbers. And sine of x is also continuous for all real numbers. So that means that h of x is continuous for all real numbers. That one was pretty simple, right? Let's see if the next one is just as simple. Cosine of x plus 1 is continuous for all real numbers. I'm going to write it differently. For all, if I can write with my pen, for all x element reals, that means for all real numbers. However, the numbers that you're going to get out of cosine of x plus 1, the range would be 0 to 2. And that's important because element, that looks like an h, element of x, the domain is x is greater than 0. It can't equal 0. So that means that we have this inside function. This cannot equal 0. So we have to find out where it would equal 0. Okay, come on. And so that would be cosine is -1 at pi, or any interval of that, or any multiple of that, I mean, where n is an integer. So that implies that h of x is continuous for all real numbers except when x equals pi, or any multiple of pi, where n is an integer. There you go. Okay, the next big thing we're going to talk about is the intermediate value theorem. This is huge. It keeps coming back up. Right now we're just kind of going to look to see how to use it, and later we're going to use it to find very specific things. So it's a lot of reading, but it's very easy to understand. Basically, you can read this on your own time, but what it's saying is if you're at this height at the beginning, and you end at this height at the end, and you have a continuous function, then you have to cross through every single y value from the lowest one to the highest one. So it's a pretty simple idea, okay? And we have a hypothesis, the if, and a conclusion. So the important connection here is we have to show that a function is continuous on a closed interval. And we'll learn the rest of this. All right, so go ahead and read through this problem here. You can pause the video if you need to. Right? So based on the 2 readings, is there a way to determine the exact time the temperature was? Right, so we don't know about that yet, but explain why. There must be a time between those 2. So do you notice there's a lot of words in this problem? That means there's usually going to be a lot of words in your answer. You have to practice explaining and justifying your thoughts mathematically. All right, so the if part of the IVT, we have to talk about being continuous. So I'm going to say the temperature has to progress. You can do something similar to this, or you're going to change the phrasing. Maybe yours is better than mine. The temperature has to progress continuously. through all the values between 47 degrees Fahrenheit and 62 degrees Fahrenheit over the time to 12:15. So at some point, the temperature must be since that lies between 47 and 62. Okay, to answer the second part of this question, is there a way to determine what time the temperature was at? Using the data we're given, no, there's no way to determine the exact time using the given data. It could have been early, it could have been later, we're not really sure. You know, the temperature could have spiked really high, then dropped down, and then went back up. I mean, we have no idea. So we're just focusing on that hypothesis by using the IVT. All right, so we have to do this hypothesis thing here. All right, determine if the IVT applies to the following function on the following intervals. Explain specifically why or why not in each case. So this is going to be easier for us to determine where this function is continuous and where it's discontinuous. So we're going to look at, we need to look at -2, we need to look at 1, we need to look at 4. And this is where these functions are discontinuous. So I start this function, I know it's going to have a vertical axis. So I'll have to find out any of the other place. So what we're going to do, we're going to check the limit from both sides. I'm going to write it because my computer's not letting me. So I'm going to check the left side, I'm going to check the right side. Okay. So the left side of -2, -2, not 2. Oh, there we go. Yeah, all right. So we put -2. Looks like we get 5 on this side, 5 on this side. So it is continuous there. Like the same thing with 1. We'll check the left side, we get 2. The right side, we get 3. So it's discontinuous at 1. And remember the function value, like we're checking that it's going to equal the same for both of these, and here we go. And then the limit from the left of 4 is 6, the limit from the right of 4 is 6. So it is continuous also at 4. So we have these two discontinuities. It's continuous everywhere else. So if we check the interval -4 to -2, yes, f of x is continuous. For all values. Okay. And something to note here with the IVT, it must be continuous on a closed interval. That's important. That'll come up a lot later. I'll try to trick you. All right, how about -3 to 0? This looks like yes, because f of x is continuous for all values on -3 to 0. C. All right, let's see. It could be, it's discontinuous at 1. But let's check this. Let's limit as x approaches 1 on the left side. I believe that was 2. Now, what is f of 1? That's 3. So no, even though it looks looks like it might be, it's not continuous. I'm going to say f of x, we should be using it. F of x is not continuous at x equals 1. Alright, make some space here. I'd like you to do this one in your words. And then letter E, 2 to 7, yeah, it looks fine, except we remember there's a vertical asymptote there. So no, f of x is discontinuous. Discontinuous at x equals 5. Alright, and so our next couple things we'll do, we'll get examples and how to use this.